Hello everyone, let's talk about exact differential equations. Exact differential equation is the technique to solve the solution to the first order differential equations of the form m of xy plus n of xy times dy dx equal to 0 for m of xy and n of xy are the functions of two variables. There are two ways that an exact differential equation can be presented. One is written with the derivative term like this equations. The other one is in differential form as m of xy dx plus n of xy dy equal to 0. So let me note here, this is the derivative form and this is the differential form. The differential equation of these forms can be derived from the level curve of the relations phi of xy equal to c, for c is an arbitrary constant. This is the solution curve that we need to determine. So in other words, if we have a solution curve of this type, we can derive differential equations of this form. And vice versa, if you have a differential equations of one of these forms, you can use exact differential equation technique to determine the solution curve. Before we can apply the exact differential equation technique to solve the solution to the first order differential equations, we need to check if the differential equation is in fact exact by testing the exactness condition. That is, we need to show the following statement is true: partial m partial y equal to partial n partial x. Therefore, it is natural for us to identify the functions m of xy and n of xy in advance. If the differential equation is exact, then we can proceed with the exact differential equation technique. We're going to see this technique through the following example. For this example, we want to determine the solution to the initial value problem of the form 2xy minus 9x squared plus 2y plus x squared plus 1 times dy dx equal to 0. This differential equation is subjected to the initial conditions y of 0 equal to negative 3. We observe that this differential equations can be written in the form of m of xy plus n of xy times dy dx, and this is not separable. So therefore, we can think about the exact differential equation technique. So the first thing you need to identify is to see what is m of xy and what is n of xy. So in this case, m of xy equal to 2xy minus 9x squared, and n of xy equal to 2y plus x squared plus 1. Before we can apply the exact differential equation technique, you need to show that partial m partial y is equal to partial n partial x. That means I'm going to take partial derivative of m with respect to y and partial derivative of n with respect to x, and hopefully they are equal to one another. So partial m partial y. In this case, we're going to treat x as the constant because we take derivative with respect to y. So I get 2x for the answer. And when I take the partial derivative of n with respect to x, I have partial n partial x. In this case, y is the constant. So I also have 2x. This gives me the statement that partial m partial y equal to partial n partial x, and therefore the differential equation is in fact exact. Next, we can apply the exact differential equation procedure to solve the solution curve to the differential equation. Here's the following procedure. Suppose there exists a function phi of xy such that partial phi partial x is equal to m of xy, which is equal to 2xy minus 9x squared. From here, I'm going to integrate both sides of the equations with respect to x. I have phi of xy equal to the integral of 2xy minus 9x squared dx. And this is the very straightforward antiderivative. And remember, because this is the function of two variables and we integrate the function with respect to x, y in this case is a constant. So the antiderivative of 2xy is equal to x squared y minus 3x cubed, which is the antiderivative of negative 9x squared. We can add a function in terms of y because remember, still we integrate with respect to x, so y is the constant. So we can add h of y at the end. The next step is to differentiate the resulting function phi of xy that you just got with respect to y, and then you match that with the function n of xy. So that is, I have partial phi partial y equal to x squared, because x in this case now become a constant and y is the variable of consideration. The middle term, the derivative of the middle term, negative 3x cubed, becomes 0, and you have plus h prime of y. You match this with the function n of xy, you get 2y plus x squared plus 1. Now you can compare the coefficients and the variable on both sides of these equations, and you see that you have x squared match with one another on both sides of the equations. What is left is h prime of y. So h prime of y will be equal to the remaining terms on the right hand side of the equations. So that is, I have h prime of y equal to 2y plus 1. And h of y is a function depends on y only. So therefore, you can integrate both sides of this equation to obtain the representations of h of y. So I have h of y is equal to the integral of 2y plus 1 dy. Now this is another basic integral problem. So the antiderivative of 2y dy is become y squared. Antiderivative of 1 dy is y, so you have plus y, and don't forget to add a constant at the end because this is the indefinite integral. So you have plus c1 at the end. Now you substitute h of y, functions you just obtained, back into the function phi of xy. So phi of xy is equal to x squared y minus 3x cubed plus y squared plus y plus c1. And now you basically set this equal to the constant because remember the differential equations is derived from the level curve, and the level curve is the function of two variables that is equal to a constant. Now I set that equal to k. You have one constant on the right and another constant c1 on the left. You basically can combine them together to have an arbitrary constant c. Or the solution curve is x squared y minus 3x cubed plus y squared plus y equal to constant c. Once again, c in this case is an arbitrary constant. So this is the general solution to the exact differential equations. You can find the particular solution to this differential equation using the initial conditions given to you in the problem. So I want to utilize the initial conditions y of 0 equal to negative 3. So that means the input value x equal to 0 and the output value y is equal to negative 3. So I get 0 squared times negative 3 minus 3 times 0 cubed plus negative 3 squared plus negative 3 equal to c. Or I have c is equal to 6. Therefore, the particular solution is x squared y minus 3x cubed plus y squared plus y equal to 6. And this is the particular solution to the exact differential equations. Now let's look at another example. In this example, we need to determine the solution to initial value problem of the form y times cosine of x plus 2x e to the y dx plus x squared times e to the y minus 1 times dy equal to 0. This differential equation is subjected to the initial conditions y of 0 equal to 0. So in this particular problem, the differential equation is written in the form of m of xy times dx plus n of xy times dy equal to 0, and m of xy and n of xy are functions of two variables and they are not separable. So therefore, there's a good chance you can apply the exact differential equation technique to solve the solutions. This differential equation is written in the differential form. To apply the exact differential equation technique, the first thing that you need to do is to test if the differential equation is in fact exact. So that is, let's first identify m of xy. So m of xy is equal to y times cosine of x plus 2x times e to the y, and n of xy equal to sine of x plus x squared e to the y minus 1. You need to show that partial m partial y is equal to partial n partial x. Partial m partial y equal to cosine of x plus 2x e to the y. Remember, when we take the partial derivative with respect to y, x becomes a constant. Now, when you take the partial derivative of n with respect to x, y becomes the constant. So therefore, you get cosine of x plus 2x e to the y, and the derivative of a constant is equal to 0. So we just show that the exact conditions is the true statement. So partial m partial y equal to partial n partial x. Next, we can apply the exact differential equation technique. That is, suppose there exists a function phi of xy such that the partial derivative of phi with respect to x is equal to m of xy, or this is y times cosine of x plus 2x e to the y. To find the representation of phi of xy, you need to integrate both sides of this equation with respect to x. We have phi of xy equal to the integral of y times cosine of x plus 2x e to the y dx. We see that y times cosine of x plus 2x times e to the y is the function of two variables, but we integrate the function with respect to x, therefore y in this case is constant. So the antiderivative of y times cosine of x dx is equal to y sine of x plus the antiderivative of 2x e to the y equal to x squared e to the y plus a function's h of y. This function is strictly a function in terms of y. Next, you need to differentiate phi of xy with respect to y. So I have partial phi partial y equal to sine of x plus x squared e to the y plus h prime of y. The next step is to match this derivative with the function n of xy. So that is match partial phi partial y with n of xy, which is equal to sine of x plus x squared e to the y minus 1. And you can see that partial phi partial y is sine of x plus x squared e to the y plus h prime of y is equal to n of xy of the form sine of x plus x squared e to the y minus 1. We observe that sine of x appear on both sides of the equations. Also, x squared e to the y appear on both sides of the equation. So therefore, you're left with x prime of y equal to negative 1. You can integrate both sides of these equations to get the representation of h of y. So h of y is equal to the integral of negative 1 dy, and h of y equal to negative y because the antiderivative of negative 1 dy is negative y, and because this is the indefinite integral, so don't forget to put the constant c1 at the end. So substitute h of y equal to minus y plus c1 into phi of xy. We get phi of xy equal to y times sine of x plus x squared e to the y minus y plus c1. And you can set this equal to a constant k which allow you to get the solution curve or the level curve. You have a constant k on the right hand side and the constant c1 on the left hand side. You can combine these two constants together to obtain an arbitrary constant c. So the solution is y times sine of x plus x squared e to the y minus y equal to a constant c. Once again, c is an arbitrary constant in this case. So this is the general solutions. To obtain the particular solutions, you need to utilize the initial conditions. So apply the initial conditions. Y of 0 equal to 0 to find c. So that is 0 times sine of 0 plus 0 squared times e to the 0 minus 0 equal to c. So c in this case is 0. Therefore, the particular solution is y times sine of x plus x squared e to the y minus y equal to 0. So in this lecture, we just go over the exact differential equation technique. Before you can use the exact differential equation technique to solve the solution to the first order differential equations, you need to show that the differential equation is in fact exact, which you need to show the conditions that partial m, partial y equal to partial n, partial x. And after that, you can follow the procedure. We are done right here. Please let me know if you have any questions.